So you cannot talk about evolution, at least the math part, without talking about Hardy-Weinberg. So the Hardy-Weinberg equilibrium hypothesizes that evolution didn't occur. Basically, this gives us a comparison to actual numbers to decide if it did happen or not. So under the Hardy-Weinberg equilibrium, in order for evolution to have not occurred, the population we're looking at can't have any mutations, cannot have any gene flow, which means that it basically can have people sneaking from population to population. And there's also no selection, again, no survival of the fittest kind of concept. And there has to be a large population, and we have to have random mating, which means the individuals don't really get a choice in who they mate with. It's just random. So when we talk about the Hardy-Weinberg equilibrium, we can use two equations to figure out our alleles, and then the other to do our genotypes. So this first equation here, P plus Q equals 1, this is our allele equation for Hardy-Weinberg. Basically, it's what we discussed in the last video, only we had a population there. In this case, we're not going to be given an entire population. We're only going to be given a small fraction of it, usually only one number of all 5 we're actually looking at on this page. Then the one on the right that looks much more complicated than it actually is the genotype. So the alleles, we use P and Q. That is very commonly used in our Hardy-Weinberg. So P is the value that we associate with our dominant allele. And then the Q is what we associate with our recessive allele. So, as I said earlier, the sum of all the things in the thing equals 1, right? So, the dominant allele is equal to a frequency. When added to the recessive allele's frequency will give you 1, or 100%. So, the same thing with genotype, but remember, with genotype, we have 3 different categories. So, I will say one thing. The way that we solve these Hardy-Weinberg equilibriums, you will not have to worry about the quadratic formula, which I think is my students' #1 panic whenever I draw this on the board. P squares and 2p and q squares, and oh my goodness, we're going to have to quadratic. We are not. These are just representing a comparison, a relationship between the 3 genotypes. So the p squared is equal to the homozygous dominant phenotype, right? So the big A. Q squared is equal to the homozygous recessive, so our little a's. And then right up the center, this 2 times P times Q is equal to our heterozygotes, which are our big A, little a's. So by using these relationships, we can actually solve for all of them if we are given one piece of the population. So the P that we see with the alleles is the dominant allele. The P here is the same P, but in order to find the homozygous dominant, we have to square that number. So if we are given P, we can find P squared. And if we can find P, we can find Q. Anyway, so it's really just kind of a trickle-down effect, one step at a time. So if you're given a value, figure out where you can go from there. So the value that I am going to give us here, our practice problem, our homozygous dominant, big A, is equal to the frequency of 0.46. So first, figure out what that is, right? Is your big A a P or a Q squared or a P squared or a 2PQ? So our big A is homozygous dominant, which means what we have been given in this problem is that P squared equals 0.46. So 0.46 is P squared. So remember, the P squared P is the same P as the P for over here for our dominant allele, but we need to get rid of the squared part. So if you remember your algebra, if you want to get rid of a square, you must square root, right? So your trusty dusty calculator will have a squared button on it. So if we want to find P, we have to take the square root of P squared. So in this case, we need to take the square root of 0.46. So 0.46 divided by, no, why did I just do that? Clear, 0.46 squared. So here's your square root of 0.46. This then means that P is going to be equal to 0.678. I remembered that correctly, right? Yes. I rounded a little, obviously, because I'm not following that many decimal points. You can't pay me enough to do that. All right, so now that we have P, right, P equals 0.067. We have P. That means we can find Q. So 0.678 plus Q is equal to 1. So do your math there. All right, 1 minus 0.678, and Q is going to be equal to 0.322. So again, double check your math, make sure that works, right? P plus Q should equal 1, right? That satisfies this allele equation. So now that we have Q, we can look at Q squared. All right, so Q squared is equal to 0.322 squared. Right, now, if you are using our lab calculator, remember that there is no squared button. If you are using your home calculator or even your cell phone calculator, you will have a squared button. But I'm here to remind you that if you don't have a squared button, you can take 0.322 times itself, right, times 0.322, and that will give you the 0.322 squared. So Q squared is equal to 0.104. So then the last number we actually need to figure out is our heterozygotes, right? So 2 times P times Q, which is as easy as taking 2 times P, which is 0.678, times Q, which is 0.322, right? And that will give us 2PQ. So 2PQ is going to be equal to 2 times 0.678 times 0.322, which gives us 0.437. So 0.437. So again, here's a chance for us to double check our mathematics. Does P squared 0.46 plus 2PQ 0.437 plus Q squared 0.104, does this equal 1? See, 0.46 plus 0.437 plus 0.104. Ta-da! Again, small rounding error, but this does give us 1.0, or we can again call that 100%. So the sum of all of those should always equal 1. And then we already did our P plus Q equals 1, right? 0.678 plus 0.322. So essentially, you can be given any number, whether it's P or Q, and you can find every single value on here because they're all proportional under the Hardy-Weinberg equilibrium. Now, if you are not solving for a Hardy-Weinberg equilibrium, right, that will not be the case. But for these examples, there is a Hardy-Weinberg equilibrium, and you will see a proportion between each of the alleles.